Hello, everyone. And the final talk of this morning's session is Vivian Kuperberg, now of Tel Aviv University, who's going to talk to us about sums of singular series and the distribution of primes. Vivian.
Thanks, James. And thanks very much to the organizers for inviting me. It's very great to be here. So I'm going to talk about sums of singular series and the distribution of primes, just like Adam's wonderful talk before me. I'm hoping that this will be very accessible, so please let me know if you have any questions. So I guess I'll start by talking about what these things are and what they have to do with each other. So the motivating question that we're going to consider, at least at first, is if we have short intervals, as we've talked about before. So we have intervals that are small with respect to n, but go to infinity with respect to log n as n goes to infinity. And we want to consider the distribution of the sums of the von Mengelt function, so the distribution of the number of primes we see in these moving intervals. And so the simplest answer to this question we can give is just a purely random model, so the Cromere model. And if we model the primes by saying that each n is independently prime with probability 1 over log n, then the distribution that we get is going to be Gaussian with mean about h and variance h log n. So we can plot this. So here's what it looks like. So in this case, I've taken h to be the square root of n, and so n is 10 to the 7th. And so we have the normalized distribution of the number of primes in this moving window. And so I've just made a histogram. And here the red line I've plotted against the Gaussian with mean h and variance h log 10 to the 7th. The moral that I want you to take away from this slide is that that's not a very good fit. And in particular, like the Gaussian guess seems pretty good. But it looks like the variance should be smaller than the Cromere guess. And so we want to look for some reason why the variance is smaller. And so, okay, so we can adjust the Cromere model. And we can adjust it by taking into account local factors at small primes. And so what that looks like in our computations is we're going to take into account the Hardy-Littlewood k-tuples conjecture. And so as a reminder, well, so we have a sequence or a tuple of distinct integers d1 through dk. And as n goes to infinity, we're going to sum over the correlation. So we're going to ask that n plus di is prime for all I. And so, right, we're taking the product, so we want them to all be simultaneously prime and summing with von Mengelt weights. And then the conjecture is that this sum is a constant times n plus little o of n. And I guess I've written this a little bit lazily in terms of admissible tuples, but so of interest in this talk is this constant s of d. So s, this is going to be the singular series at d, that's what the constant is called. And it can be written as a product of primes of 1 minus nu d of p over p divided by 1 minus 1 over p to the k. And so at each local factor from a probabilistic viewpoint, we can think of this as correcting the random model. And so if we need n plus di to all be simultaneously prime, then for a small prime p, we want n plus di we want none of them to be 0 mod p. And so if you were assuming that the primes are all independent, then you would guess that n plus di are independently non-zero mod p with probability 1 minus 1 over p. And so the probability that none of them are 0 mod p is 1 minus 1 over p to the k. But okay, it's not independent. And so if we consider the set as a whole, the probability that none of the n plus di are 0 mod p is 1 minus the number of, or 1 minus nu d of p over p, where we want to think of nu d of p as the number of congruence classes mod p that n needs to avoid for none of the n plus di to be 0 mod p. Okay, so if we use the Hardy-Littlewood conjectures in variance computations, so we can compute the variance with this sum and just expand the square. And what happens, so we want to think of this as a sum over von Mengelt functions and then expand the square when we're subtracting off the mean. And what happens when we expand the square is that we get a sum over correlations of different integers being primes with a fixed difference. And so then we can analyze those correlations by using the Hardy-Littlewood conjecture. And so, okay, so there's a little bit of a longer computation, but what you get out is a sum over singular series if you apply the Hardy-Littlewood conjecture. And so then this sum over singular series, I guess it was known before, but with the constant term, this was computed by Montgomery and Sound. And so inputting this, understanding the sum over singular series, we can get that the variance should really be h log n over h plus b minus 1, where b is this explicit constant. So in particular, this is smaller. It's smaller in a couple of reasons. For a couple of reasons, one is that this, or I guess b minus 1 is a little bit negative. So the constant term is negative, but also we're subtracting off h log h. And so that's substantially smaller, especially when h is on the order of the square root of n. So we can plot this. And here we have the green curve, which, okay, I guess it's not showing up as well as I would hope, but I think it's still visible. And you can see that it's a much better fit.
Can you turn the mic on?
Out of curiosity, what is the significance of b versus b minus 1? I mean, I think there was like an added 1 in the definition of b. Is there a reason for that?
Right. I think this is the minus 1. I mean, right. So b is this constant that comes out of understanding the sum of singular series, and then if you and the minus 1 is from elsewhere in the variance computation. So it's
one way to think about is when you integrate log t up to x and look at the average, it's log x minus 1. Right. So that's
right.
The natural reason.
Right. Yeah. So just by integrating log t, you get another natural reason to get a minus 1 out from doing the integral. Yeah. Okay. So the moral of the story is that if we sum the singular series for different d, we get information about the distribution of primes. And so if we're summing singular series as the set varies, then we can learn things about the distribution of primes. And so in fact, in Montgomery and Sound showed, assuming the Hardy-Littlewood conjectures, and in fact, assuming a form of the Hardy-Littlewood conjectures with a stronger error term than what I put on the previous slide, that the distribution of primes in these short intervals approaches a Gaussian distribution where the variance is h log x over h plus b minus 1. And so their work, I mean, I guess this is a sort of variations on a theme, but once again, it's the moments method. And so they computed the moments, and crucially, they were computing sums of singular series in order to understand the moments. So the sums that they considered, so instead of the singular series as I stated it before in the previous slide, they considered S naught of D, where it's just an alternating sum over subsets. And in particular, this is effectively subtracting off the mean at the beginning of the problem. So if instead of considering correlations of the von Mangoldt function, you consider correlations of lambda of n minus 1, so that it has mean 0, then you see these singular series arise naturally. And so we take Rk of h, which is a sum over all sets of k distinct integers between 1 and h of this S naught of D, where I guess I haven't written it, but D is this set of D1 through dk. And then for any integer k, Rk of h is given by mu k times negative h log h plus b plus 1. This is the same constant b times h to the k over 2. And then there's an error term, which is there's a constant depending on k and epsilon, but h to the k over 2 minus 1 over 7k plus epsilon. So here these constants mu k are exactly the Gaussian moment constants. So it's this product of the odd numbers up to k when k is even, and when k is odd, it's 0. Okay, so there's various things to notice about this, but one point here is that in the error term, so this minus 1 over 7k is sort of not particularly convincing as an asymptotic. And in particular, when k is odd, we don't even have a main term. So we don't know the asymptotic size of this sum of these sums when k is odd. And when k is even, we don't understand the second order terms. So I have this conjecture, which was originally formulated in the paper of Lemke, Oliver, and Sound on the bias in the distribution of consecutive primes and arithmetic progressions, which is that when k is odd, Rk of h should be asymptotic to h to the k minus 1 over 2 log h to the k plus 1 over 2. So, so I guess going back, here the main term is of size h log h to the k over 2. When k is even, and so in the odd case, we expect an extra sort of square root of h saving in the h factor, and then we lose a power of log. Okay, so I've plotted this on a computer in the case when k is 3. So this is for h between 0 and 20 and 200,000. No, I think that's a typo. It's 20,000. So here's R3 of h in black, plotted against 0.37 or so. It's a constant that I optimized numerically, so it's about 0.37 h log h squared, which is dashed in red. And I guess, yeah, okay. So when I give this talk on an iPad, or when I show this chart on an iPad, I had a thin red line, and I would say, if you can't tell that there's two different lines, let me zoom in. But I can't do that here, so I made the red line thicker. But in fact, it's just a very good fit. And I guess I will say, so this constant is a little bit tantalizing. It's sort of close to various things. You might guess there's an Euler product expansion for it, but I don't know of a reason why this constant should be correct. It's quite close to 1 over e. It's also quite close to 3/8, and sort of both of these seem like reasonable guesses, but I don't know. Okay, so as further evidence for this conjecture, so I have the following bounds. So for starters, when k is 3, I can show that R3 of h is at most of size h log h to the 5th. So in particular, this is the correct power of h. And remember the previous bound for odd k was on this size, h to the k over 2 minus 1 over 7k plus epsilon. Now also by considering the same problem in the function field case, I was able to get a bound when k is 5. So I haven't gone through much of the setup, but if you're wondering if something is sort of identical in the setup or not, it probably is identical. So in this case, we have like the same RK of h, which we want to think of as the sum over the singular series, which is defined in the same way for distinct polynomials in FQ adjoint T. So I guess I haven't put it on the slide, but I also have a bound when k is 3 in the function field case, but I can go further and get a bound when k is 5, which has the correct power of h as well. So h squared in the case when k is 5. Okay, so I'm going to talk about other things, so I'm not going to say very much about the proof of these results, but I will just say briefly that after a little bit of work, it sort of comes down to this question about adding fractions. And 3 is sort of not a very big number, and so 3 fractions are sort of manageable. And 5 is a bigger number, and 5 fractions are much, much more difficult, but in certain ways, the function field case is nicer. So that's what I'll say about that. But what I want to talk about is sort of a heuristic for how to understand these sums. And so this heuristic doesn't govern the proofs. In fact, the heuristic really sort of, I don't know how to make it work to push through to a proof in any case, but it's a good heuristic nonetheless. So we're gonna use the notation that E of alpha is e to the 2 pi I alpha, and the sums Rk of h admit the expansion that Rk of h is a sum over Q1 through Qk, which again, I was talking about fractions earlier. We want to think of these as denominators, Q1 through Qk. And then we have this weight factor, which is this product. So for each I, we get the Mobius function at Qi divided by Euler's quotient function. And then we have an inside sum, which is a sum over numerators, A1 through AK. Right, so okay, so they're numerators, so we want our fractions to be reduced, and AI is between 1 and Qi. And then we want the sum of all of our fractions to be an integer. And this is sort of the crucial constraint on these fractions. And then we have an inside sum, which is our sum over our sets. So we have a sum over D1 through DK up to H, which are distinct. And then we have E of A1 D1 over Q1 through E of AK DK over QK. So, okay, it's talking about how 5 is a big number. So let's go down to k equals 2. So here, this is exactly the same expansion. But I've just replaced all my k's with 2's. And again, this crucial constraint is that a1 over q1 plus a2 over q2 is an integer. And so in the case when k equals 2, we can understand this very well. We can understand these fractions very well. And so in this case, q1 has to be equal to q2 since our fractions are reduced and the numerators are opposite. So this tells us, so just I've just sort of plugged this in and deleted some of the terms in the sum that are determined. And we get a sum over q and then a sum over a, and we have d1, d2 distinct. So if we consider this inside sum over d1, d2, it would be very easy for us to understand this if we didn't have the constraint that d1 and d2 were distinct. And so we can split this into a sum over a complete sum and then subtracting off the terms where they're equal. And then more or less, we want to think of the complete sum as having a lot of cancellation, and the terms where they're equal give something of size about h. And this thing of size h is sort of what's going to give the square root cancellation more or less in the size of this sum. So, okay, so now we're through the heuristic in the case when k equals 2. And the moral in this case is that in general is that in a somewhat heuristic way, requiring distinctness of d1 and d2 provides the main term. So in particular, this h contribution came from the fact that we were requiring the distinctness, and when we got rid of it, we showed up with this. And so we want to think of we really want to think of the main term as coming from the fact that we're requiring things to be distinct. And I'll say that for even k, the main term comes from splitting up the terms qi into pairs and recreating the case k equals 2 for each one of the pairs. And so it's hard to deal with 4 fractions, but it's easier to deal with 2 fractions twice. And that's what gives the main term. So for example, we can say q1 is equal to q2 and q3 is equal to q4 and so on. And there are mu k such pairings for all k. And so that's where that constant comes from in this moment computation. Okay. So I guess the other thing I want to comment on is that you can also sort of run this heuristic when k is odd. But yeah, I guess I don't know how to turn it into an asymptotic, even in the case when k equals 3. And there's also something sort of somewhat annoying in the computations where, okay, I might have a mistake. I hope I have a mistake, but I've been getting a constant of 1/4 when I compute the heuristic for k equals 3. And my code gives this constant of 0.37, which might be 3/8, but we don't know. Certainly not 1/4. So, okay. But for the rest of the time, I want to talk about something different, which is a result that really sort of speaks to the strength of this heuristic, even though in many cases it's not working for me. So the question is, what happens in a sum where the pairs di, dj will be distinct without being forced to? So again, in this heuristic, we were saying that the main term was coming from the fact that we were requiring distinctness of the di, dj. Okay, so what do I mean by this question? So let's fix a modulus r, and congruence class is mod r. And so then for for a set d1 through dk, we want to define the singular series sort of away from R, where we just consider the other terms in the Euler product, for the following reason, which is that we're gonna take a similar sum, but we require the ith element of our set to be congruent to Ci mod R. So the terms with p dividing R are just already determined by this constraint. And once again, we have this S naught where we're doing this alternating sum in exactly the same way. So this is just still a sum over singular series, but we want to require that the ith term of our set is determined mod R for some fixed thing. And so if Ci is not equal to Cj mod R, then Di is not equal to Dj already without the extra distinctness constraint. And so we might expect that turns into something sort of smaller in the asymptotic if we have many congruence classes mod R that are already distinct. And again, this is sort of because our heuristic told us that the main term, the main contributions to this sum over singular series come from the distinctness of the DIs of this result. So first, let's consider the case when k equals 2. So if k equals 2 if C1 and C2 are not congruent mod R. Then we get that R2 is of size h. So not h log h as we saw before, but of size h, where, okay, there's some constant. I haven't put it on this slide, but okay, it's an explicit constant. I just haven't written it on the slide in terms of R, C1, and C2. And meanwhile, if we have convergence classes that are distinct, are congruent mod R, so in this case, we would expect something bigger, and that's what we get. So we get a main term of size h log h. And then there's also a constant term with an explicit constant. And partly to convince you that my other constant was explicit, I wrote this constant on the slide. So this is the case when k equals 2. And just as before, so this extends. So for k greater than or equal to 3, okay, let's take k even. So up to an error term that's smaller, and it's the same error term that was in Montgomery and Soundararajan result, which is not a coincidence. Rk of h, R, C1 through Ck is a sum over pairings of the Ci's, and the growth rate is governed. So the growth rate in each term is governed by the number of pairs that have matching Ci's. So if right, okay, so let me sort of say a little bit more about what that means, because it's a little convoluted, but the idea is that we're summing over pairings just as we were summing before. And so we have, okay, so I have this example when k equals 6 and R is 10, and let's say that C1 through C6 is 1, 1, 3, 7, 7, 9. So to sum over pairings, so let's consider one such pairing. Okay, so this is going to be one term in our sum. And then for the size of the term is going to be h to the k over 2. So in this case, h to the third times a power of log h, and the power of log h is obtained by just counting the number of edges where the number of edges in this pairing where there's the same value on either side. So for this pairing that I put up here, 1 and 1 are equal, and so we get h cubed log h because none of the other two. But this sum also has terms corresponding to this pairing, which has size h cubed because none of the edges match, and this one, which has size h cubed log h squared. Yeah, I guess, okay, there's also constants, but they're more complicated.
So in the prior slide, you had that explicit constant, which was in the expansion for C1, or one of the residues, but it didn't depend on C1.
Right.
And in I guess the other constant that's not shown, it does depend on both C1 and C2, not the difference or something? It
depends on the difference, yeah. Yeah, so, right. Yeah, so this is a good question. So in fact, I've written that this depends on C1 and C2, but it actually just depends on C2 minus C1. Right, and C1 minus C1 is 0. Or, yeah, fixed at least. Okay, so right, so we get these pairings, and again, really, like the moral of the story that I want to emphasize here is that this really supports the heuristic that I gave before, which is not how any of the proofs go, but it's an instructive heuristic, in the sense that here really these like log h's in each of these terms. So the contribution to the growth rate in terms of h is really coming from how many terms we're forced to break instead of having them broken for us. How many opportunities there are for collisions that we have to avoid. So I think I'll stop there. So thank you and happy birthday, Andrew.
Great, thanks a lot. So questions for Vivian?
Do you have any lower bounds on your R case for odd k?
For the odd case, no. I would love a lower bound, but yeah, I mean, again, this heuristic argument gives an asymptotic, and the asymptotic is a quarter h log h squared, but it's a heuristic argument, and I can't get a lower bound.
It's a bit naive, but do these higher moment conjectures have any relation to pair correlation for zeros?
Yes, right. Yeah. Yes. So in fact, this right. So the result of Montgomery and Sound is well, okay, with sort of appropriate error terms is effectively equivalent to pair correlation.
think that the secondary term was got, isn't the secondary term proved through zeros by Peng-Gao maybe?
Yeah, I believe that. Yeah, that sounds right.
So if you have some tertiary terms.
It's Seho-Chan. And what he did is corresponding secondary terms and factorial.
So what will you use these results for when you get stronger results?
Right. Well, yeah. So, okay. So that's a good question. So, yeah, I guess I mentioned, okay, maybe I won't flip back to it, but, so computations are, I mean, okay, so there's various applications. I think one of them that's sort of interest, but still a little out of reach is looking at lumped Gallagher and Sounds results on the distribution of consecutive primes in arithmetic progressions. And in particular, sort of trying to put their heuristic derivation on firmer footing. And so, so in fact, they're using both some of the stuff with sums of singular series and arithmetic progressions, and also some estimates for the odd case. But okay, I guess more k=3 than the other odd cases.
Any final questions for Vivian? Seeing no final questions, let's give Vivian a round of applause. And now we'll give another round of applause for all this morning's speakers.